Hello and welcome to my channel. I'm here to explain you about the sampling theorem. We will discuss what is sampling, aliasing, and finally understand the Nyquist-Shannon sampling theorem. But first, let us understand what is sampling. Sampling is related to conversion of analog signals into digital signals. There are mainly three steps in the process of analog to digital conversion: sampling, quantizing, and encoding. Sampling is the first step in this process. Now, as we know, analog signals are continuous in nature. Everything we hear or speak is a continuous signal, but the electronic devices we use, like our smartphones and laptops, cannot process or understand analog signal, so they need to be converted into digital signals. For that, we need to collect samples of information from the original analog signal in order to convert them into a stream of digital data. And that's basically what sampling is. It is the reduction of a continuous time signal to a discrete time signal. Now, to understand this better, let's take an example of a sinusoidal wave. As you can see, this is a continuous analog signal which is represented by amplitude on y-axis and time on x-axis. Now, in order to perform sampling, we need to multiply this signal with a periodic impulse train which looks like this. The period of this signal will be the sampling interval t of our sample signal. Now at the output of this sampler, we obtain the required sample discrete signal which looks like this. The sampling frequency or sampling rate fs is the average number of samples obtained in 1 second. Thus fs equal to 1 by t. This signal contains sample information of the original analog signal. If we join the values of this discrete signal, we can successfully obtain the original signal. But what happens if we change the value of t? We obtain a resultant signal that has a different sampling rate. Now if we try to reconstruct the signal, we see that it's not quite accurate as before. This effect is called aliasing. Aliasing refers to the distortion or artifact that results when a signal reconstructed from samples is different from the original continuous signal. Now, how do we deal with this problem? There must be a minimum sampling rate at which we can successfully recover the original continuous signal, right? Well, that's where the sampling theorem comes in. The Nyquist-Shannon sampling theorem states that a continuous time signal can be completely represented in its samples and recovered back if the sampling frequency fs is greater than or equal to twice of the maximum frequency component present in the signal. The minimum sampling rate, which is fs equal to twice fm, is called the Nyquist rate. If we consider this signal, which is represented by the equation y equal to sin pi t plus sin 4 pi t, it has two frequency components, f equal to 0.5 Hz and f equal to 2 Hz. So here 2 Hz is the maximum frequency component fm. So the sampling rate fs should be greater than or equal to 4 Hz in order to accurately obtain the original signal. One thing to note here is that the continuous signal must be a band-limited signal. A band-limited signal has no frequency component above a certain maximum frequency. It may be a low-pass spectrum or a band-pass spectrum. So, in order to apply the sampling theorem, the signal must have a maximum frequency limit. In fact, everything we hear through our ears is a band-limited signal, because as you know, our human ears cannot hear frequencies more than 20 kHz. So according to sampling theorem, audio signals must be sampled at a rate of 40 kHz or more so that there is no loss of quality in human hearing. One practical example of sampling can be seen in this digital audio waveform. If we zoom in, then we can see the individual samples of the digital audio file, which is sampled at 44.1 kHz, which is one of the common sampling rate of digital audio. So that's all in this video. I hope that I have given you some basic idea about sampling and sampling theorem. If you have any queries, leave a comment down below. Thanks for watching.